All right, so we'll take a look at a few of these cellulosic materials, specifically the ones that are related to from the viewpoint of fire. And we'll see three types here. We'll take a look at cotton, papers, and wood. So take a look at cotton first. So cotton, commercial cotton is derived from the cotton plant, um, and it's more than 90% cellulose. So where do you find these? Obviously, you find them in upholstery, maybe from mattresses and stuff like that. Um, and again, this is just related to where you would typically find them contributing to fires, for example. You also find them in places like padding for the upholstery for furniture. And then obviously clothing be a big place where you find cotton products. Papers, probably the most dominant molecule or substance in paper is going to be cellulose. There are other things that are added to the commercial paper, for instance, but cellulose um, is the main ingredient. Other things are added to to increase the paper's strength, for example, to make it brighter, color, and etc. Paper starts to decompose at around 230 degrees Celsius, so roughly 450 degrees Fahrenheit, and most um, completely decompose at about 700 degrees Fahrenheit. So again, substances that are primed for fire essentially, and then we have wood and wood materials. So obviously there are many, many different types of wood that exist and have different characteristics, different physical properties. Densities, for example, can be different, ranging from, half a gram per mil to maybe 0.75 grams per mil. The chemical composition of the wood also varies depending on where the wood comes from. And the chemical components can vary. So for example, there might be 40 to 50% cellulose is what it ranges for in wood. There's about 18 to maybe 35% of something called lignin, which is another type of molecule. There's about 10 to maybe 30% of something known as a hemicellulose, which is kind of a relative of cellulose. There's about 5 to about 20% of extractives is what they're referred to as. So these are things like oils, tars, etc. In there. And then there's a small percentage, less than 1% of things like minerals. It's just some other components here that make up um, the remaining part of the wood. So with all of these examples that we've looked at, these are cellulosic, right? So they're based on the structure of cellulose, which is a polymer of glucose. And as we've seen, when you burn a hydrocarbon, or in this case, a hydrocarbon with oxygen in them, when they undergo complete combustion. So in other words, if there is, more than enough oxygen available, typically what we're going to get is carbon dioxide, and we're going to get some water vapor as well. Now, when do you have complete combustion of stuff in a fire? Well, maybe not all the time. Sometimes you're going to get some carbon, some soot, some smoke, some carbon monoxide, depending on the degree of combustion, whether it's complete or incomplete. But if you have something that contains carbons, H's, and O's, and you burn it, right, these are the typical products you're going to get under complete combustion. So incomplete combustion can also produce carbon monoxide. We can also get just carbon, for example, in the solid form, which is just the particles, soot, char, for instance, that you see coming off. Now, there are other natural materials. So we just looked at the cellulosics, but there are other ones, other natural polymers. And we're not going to go into an exhaustive list of these, but things like, for instance, wools, maybe leathers and silk materials. These are animal-based materials, animal-based polymers, and these have a high protein content. Okay, we talked about proteins before when we introduced polymers, natural polymers in the first place. Proteins are also polymers, as you recall. And these are polymers of not sugars or glucose. These are polymers of things called amino acids. These are the building blocks of proteins, amino acids. Write that down. So amino acids. And the thing about amino acids that is different, there are several things that are different than glucose, for instance, um, is that these amino acids are going to contain, in addition to carbon, uh, oxygen, and hydrogen, we're also going to contain nitrogen, and some of them also contain sulfur. And the presence of these then is going to give a different characteristic to these substances when they burn. So that their chemical properties are going to change because of the presence of these nitrogens and sulfur. So before we get to that, how are these amino acids linked together in the first place? These are connected via what are known as amide bonds. Okay, we saw amide bonds in our functional groups before. Amide bonds are also known as peptide bonds. Okay, and as a quick reminder, the peptide or the amide bond is going to look like this. You have a C double bond O connected to a nitrogen, right? And that is what makes it an amide or a peptide. And that's what you have in every single protein. So it's going to have nitrogen, definitely, and then a little bit of sulfur in there as well, depending on the building blocks of the amino acids that you have. So these, because you don't have as much oxygens in them as a carbohydrate, yes, they will burn, but they are less flammable than cellulosic materials. But they do burn in air under elevated temperatures, right? So they do burn, but they're less flammable because we have the presence of nitrogen atoms in these proteins and protein-based materials. Their thermal decomposition can include nitrogen containing. So when burned, in addition to all the other products you mentioned before, these will also produce nitrogen-containing irritant and toxic gases. Okay, so for example, you can get ammonia, NH3, you get hydrogen cyanide, HCN. So definitely, combustion of these things produces additional gases that are inherently more dangerous than carbon dioxide or water vapor. The presence of sulfur in some of these protein polymers as well can produce additional products as well. So these would produce sulfur containing gases, typically oxides of sulfur, like sulfur dioxide, SO2, etc. And those are also inherently more poisonous or more toxic to living things than carbon dioxide or water vapor. So point here is the burning, or when these things catch on fire, right? The products that you get are going to be different depending on what they are made up of. If it's a cellulosic material that's based on glucose, lots of C's, H's, and O's, right? We're going to get a bunch of carbon dioxide and water vapor. If there's complete combustion, we'll get maybe some carbon monoxide, maybe some soot, some regular carbon if there's incomplete combustion. Protein-based materials are going to have additional toxic products like oxides of nitrogen, oxides of sulfur, etc. So those are the natural polymers. We'll take a look next at some of the synthetic ones.